Okay, people are coming. It's raining outside. Thank you so much for coming to this great colloquia today. And it's really my honor to introduce our colleague, Professor P.S. Krishnaprasad, who is our last speaker of the semester. Just to remind everyone, ISR Colloquia is sponsored by IAI and is in every first Wednesday of each month. So we'll resume our schedule again in February. So please stay tuned. We will announce the next round of seminars. Just a brief background information to my very dear colleague and friend, Professor Krishnaprasad. Krishna has been with the University of Maryland since 1980, where he has held the position of a professor in electrical and computer engineering department with a joint appointment in the Institute for Systems Research since 1988. He's also a member of the Applied Mathematics faculty. Krishna has held a number of visiting positions with the prestigious institutions such as University of California, Berkeley, Erasmus Universities, University of Göttingen. I mean, the list is long, Cornell University, and Princeton University, and so forth. Over the years, his research interests lie in the broad area of the geometric control theory and its applications. His contributions include geometry of parametrization problems in linear systems, the Lie algebraic foundations of certain nonlinear filtering problems pertaining to systems identification, and also applications that involve with the interconnected mechanical systems, such as a spacecraft with elastic attachments, spinning rotors, and some other examples that you're going to listen and learn today from his seminar. Krishna is a fellow of the IEEE. He was appointed the 1998-2000 Distinguished Faculty Research Fellow of the University of Maryland. And he has a recipient of many awards, including the prestigious Hendrik W. Bodie Lecture Prize for 2007 from the IEEE Control Systems Society. It is really my honor to introduce him today, so please welcome Krishna.
Thank you, Reza, for that most kind introduction, and thank you all for coming. I hope you will find some aspects of this talk, each of you, of interest to you from your own perspective. The perspective of mine happens to be that of exploring how to extract information of a detailed sort from observations of collectives. By collectives, I'm thinking of the things that we all encounter on a daily basis, groups of birds, groups of people as well. And when we observe them, we watch them, we perhaps get snapshots of information about them. We want to extract more detailed information than what the snapshots are telling us. So how do you do that? So this is really the fundamental problem of reconstructing of collectives. And it shows up in a variety of contexts, but I will illustrate that shortly by a few videos. So before I continue with the talk, I would like to acknowledge gratefully the support I have received over the years from AFOSR, most recently through this grant, and from an ONR Muri grant dating back to 2007 that has been a resource of support for students as well as myself in a collaborative environment in ECE. So the outline of my talk is going to be, first I'll give you a little bit of motivation in the form of a few videos that set the physical context in mind. And then I will formally state what I mean by the problem of data assimilation, which I refer to in the abstract. And then after that, in that context of data assimilation, I will discuss a class of models that I will call generative models. And associated with these models and empirical data, there will be an inverse problem. And to each such model, there will be an inverse problem. And the idea is, how do we solve this inverse problem? In some sense, this is the problem of reconstructing collectives. And so the perspective I come to in this context is very much rooted in my own experience, and that is to think about these inverse problems as optimal control problems. And equivalently, one can think about them as complicated nonlinear optimization problems or nonlinear programming problems. And there are advantages to viewing this in one way or the other, computationally as well as by way of understanding. So I'm going to discuss that, and following that, I move to a broader setting of where geometrical ideas apply, and then there are some familiar things like finding shortest path between 2 points in a physical space, as well as slightly less familiar things. And all of these constitute a geometrical way of thinking about taking data and smoothing it out and removing the noise, and then from that being able to find the underlying truth that the data is reflecting, okay, to the extent possible. So this is the setting in which my talk is set up. So I'm going to show you 3 videos. The first one is a video of flocking by starlings. And this video was taken by an ordinary handheld camera, video camera. And but when we want to take actual data from such flocks, then the colleague Andrea Cavagna, who provided this video from the Institute for Condensed Matter Physics in Rome, he and his group have been working with multi-camera networks which are set up on rooftops in Rome, and then these are synchronized, and they are high-resolution cameras. You'll see why they need to be high resolution, and as a result, there is a trade-off between resolution and sampling rate. So it is coarsely sampled, as you can see, and more recent versions of this project lead us to better sampling rates, namely you can get as much as 60 frames a second. And the creatures in these videos, namely starlings, European starlings, they move fast, for anywhere from 8 to 18 meters per second, and if you want to observe them, you have to have reasonable sampling rate as well as reasonable resolution, as you will see. And this is an important set of difficulties that one has to face. So I'm going to show all 3 videos in succession off of the main talk slide, and instead straight out of so here it is. So you're hearing Andrea in the background speaking in Italian, and so you see a flock, and then you see a peregrine falcon going after them. It is a very effective predator. The flock is in some sense trying to move in ways that cause it to escape from the peregrine falcon, or at least some of the flock members. And as you can see, the falcon is trying pretty hard, and the movement of the flock involves being attacked, then it splits into parts, and then merges again, and that's the sequence you will see. And it's quite dramatic, and the shape of the flock changes over time, but deeper analysis reveals that for the most part it is essentially like a pancake. It's nearly two-dimensional in nature. And so it's split, and then they merged, and to some extent the falcon has gotten tired, and then it comes back to attack it. All right, so that's just to give you an idea. So you can see that a typical flocking event has a number of birds in it. So we have data sets in which we have anywhere from 150 to 700 birds, and the actual flocking events can have many more. And they occupy a relatively small space, which means then that to resolve the individual birds takes a high-quality, high-resolution camera system. And that is the source of the trade-off, namely to get such a camera system, you need to trade the frame rate. So that's the first one. And then the next one I'm going to show you is a video that many of you have seen. So instead of thinking about flocks, you can look at individuals in the flock, for instance. So here, instead of thinking about birds, we're going to think about mammals, in particular bats. And this video is actually taken in a laboratory just down the street from us in the bioscience, in the psychology biology building. And there, in Professor Cynthia Moss's laboratory called the Auditory Neuroecology Laboratory, they've been studying the behavior of bats behaving in situations such as prey capture, capturing insects. And they've been studying this using tools of infrared visualization, because it's a dark room, you use infrared cameras, and then observe the bat moving about and going after the target. And how does the bat know where the target is? It puts out ultrasound, sonar, and receives echoes, and then from that it knows the range to target and direction of target and chases it. And you'll see a little bit of this. And so on the right you're seeing a MATLAB animation done by post-processing. The fan beams that you see are synthetically constructed, indicating which way the bat is looking. And in this portion of the animation, you can see that the bat managed to capture the target, and that's essentially what I wanted to leave you with. There's many more details one can talk about in this context. So I'll give you a little bit more of the context when I go back to the slides. Then the third one is from the insect kingdom, and it is a video supplied to me by a professor who visited the University of Maryland back a year ago or so, and is Robert Olberg from Union College in Schenectady, and he has devoted a major part of his life to the study of dragonflies. So you're going to see here a dragonfly sitting on a perch right here, and there is instead of a fruit fly flying by that it would go after as prey, you'll see a bead being moved artificially, and they'll cast a shadow on these leaves. And then this guy is watching at least halfway through this animation, and then simply turns his head. He has assessed which way the bead is moving, and then he launches himself, and then goes after the bead and captures the bead by its four legs. And all of this happens within a couple of hundred milliseconds, and so all of it is highly slowed down. And so let's play this and see what it does. Alright, so it started. So he is still very quiet, moving his wings a little bit, and then he's starting to turn, as you will see when the bead comes into view. And it's a very visual creature equipped with these, see, you got it. And these arrows were put in after the fact, and you see the bead trajectory is not a straight line, it is a curvy trajectory, and this is telling us which way the dragonfly is looking. So all of this was done with the help of post-processing and a fixed camera, video camera. But if you want to take any positional data of this sort, then you have to have multiple cameras so that you could actually not only get XY information, but also depth information. So from that, you'll be able to get that at the frame rate. So, for instance, for video number 1, for the star length, the frame rate was low. For the bat video, the frame rate is much better, 240 frames a second. The speed of the individual in this instance is about 2 meters per second, or a little more, and it goes after a fixed insect or a moving insect. And if you study such bats in a big swarm, then it's even more challenging because they're all vocalizing, they are beating their wings, and you could easily see occlusions and stuff so that you don't know which bat is which and cannot keep track of it. But those are all challenges for field work. In the laboratory, you do this with just one bat and one insect, and it gets to be a lot better. Although in Moss's lab, they have worked with multiple bats doing both competitive prey capture and other kinds of behavior. And so in the video from Dr. Oberg, and also some related work by Dr. Anthony Leonardo out at Galeria Farms, which is one of the campuses of the Howard Hughes Medical Institute, there are tools available that allow us to take observations of dragonfly flight and prey capture behavior at 1,000 frames a second. And so you can get a lot of data, but still, as I said, much of the action takes place in a very short amount of time, namely the actual prey capture events. So if you want to know the details, then you need to somehow get inside what is happening between the sampling instance. Okay? So you have to recover somehow a good approximation to the continuous time behavior out of this sample data. So that's, in a sense, a fundamental problem of collective, fundamental problem of reconstruction. So now I get to define what I mean by data assimilation. So extracting a suitable model, and the model is expressed in continuous time settings with input. And so you have to extract the model and the input from sample data. The models I'm going to show you will actually be completely determined once you plug in the input, so there are no free parameters. So there's no parameter estimation problem associated with this. It's actually an input estimation problem. And then not only do you want to extract the input, you want to interpret the input. So you want to know how the input relates to some possible sensory information the dragonfly or the bat or the starling is gathering from its environment. So in other words, you want to uncover the feedback loss or mechanism governing the trajectory of the creature. So for instance, it could be the feedback loss that governs curvature of the trajectory as a function of sensory data. In the case of prey-predator interaction, such as the bat-insect situation, is the location, i.e. range and direction of the target that the bat needs to know from its vocalization, and then how that information is converted to the steering action by the bat, and that essentially obtained at a certain abstraction, which does not involve all the biomechanical details of the bat. That's really important to keep in mind, because to get to that level of detail is very challenging. Now, in the case of flocks of birds, you may think about the bird, one bird of interest, say a focal bird, observing a bunch of birds. Not all of them are taken into account. Only the ones that are in a certain neighborhood are paid attention to. And then you want to ask, what strategy does a focal bird adopt based on relative locations of its neighbors? So these are all things that we want to find out. And so I want to think of data assimilation as the problem of taking sample data and extracting this type of information. So now the word data assimilation is used elsewhere in the literature, such as in atmospheric sciences, in meteorology, etc. Also in a somewhat similar way. Perhaps there are differences having to do with the very fundamental physical nature of the models that are associated with those fields, such as Navier-Stokes equations and thermal equations and whatnot. But in the present context, we are using data assimilation as a problem of figuring out what the generative model is and what, within the class of generative model, extracting inputs. So we, in the course of time, over various bodies of work, zeroed in on one class of generative models that is expressed here. There are two sets of equations. They only differ in a subscript E or P, E standing for evader and P for pursuer. And what they reflect is equations that govern two particles emanating in space somewhere and then moving about and tracing out trajectories, a dotted trajectory or a solid line. And associated to each of these trajectories, we have a bunch of equations that are really pretty much the same information as, essentially the same information as in Newton's equation, but written in an odd way. So what is the oddity? Well, the position variable gamma is expressed as a certain normalized velocity vector x multiplied by nu, the speed. Okay, so that's the first obvious equation to write down. So as soon as I give you a normalized velocity vector x, then one can think about two other vectors, y and z, that give us an orthonormal triad. Okay, so they form basis vectors in the space that's perpendicular to the vector, which is the velocity vector. So then one can write down equations of this form, but what we are saying is that we can describe how the triad of vectors x, y, z, unit vectors, evolve along the curve. So this is what we call a moving frame. So as you watch the particle move along the curve, then this triad of vectors moves with it. And the main point of this slide is that given any curve, reasonably smooth curve, in fact only twice differentiable curve, you can associate to it such a moving frame or triad of vectors along it. And then as you notice, there are some extra symbols. Nu is denotes speed, but little u and little b in italic font are really two curvatures, natural curvatures associated with the curve. And these are related to classical notions of curvature, such as 1 over the radius of curvature of a curve at a particular point. And by a simple formula, a lot like the representation of information in polar coordinates. In other words, u squared plus v squared, it ends up being the square of the classical curvature. Okay? And the classical torsion information can also be recovered from this. So the point of this is then that there is, unlike in what's known as the Financier A-frame, which everybody encountered in calculus, this concept of frame is essentially unique in the sense that once you pick an initial frame, then this set of equations propagates. So the inverse problem aspect of this is that if now I have not this curve, if I have this full curve, no sampling, can I recover the curvatures? So you think about curvatures here as actions that the particle, which is moving along the curve, which is an agent or an animal or a bird, what have you, the action that it takes. So if you think of these as so-called self-steering particle, and I want to know what steering actions the particle took as it moved along. To recover that, there's a bunch of equations one can write down, and they actually, as I said, essentially uniquely determine the curvatures. The only ambiguity is a certain directional ambiguity in the initial conditions. Okay? And it's so 1 degree of freedom, or drilling freedom as it is sometimes referred to. And, okay, so then the idea is that this is not the world we are living in. We never get to have the full curve. We have the sampled curve, either obtained via video or stationary cameras or other devices. Okay. So this is a generative model, and I want to also, at this stage, before I go further, point out this generative model which looked, well, there are two sets of equations, but only one set of equations we need to care about for one agent. And there are two here because there are two agents, one evade and one pursuer. But we can write these in a compact matrix notation. And the matrix notation is of the following form. The XYZ can be packed into a little block 3x3 rotation matrix. The gamma, the position vector, can be put in this place. And then we did that, this 4x4 matrix is what is known as a rigid motion matrix, an element of the rigid motion group in 3 dimensions. Nu is, of course, the speed, and the u and v are the natural curvatures. And if you now define these standard 4x4 matrices, they play the role of infinitesimal translation, infinitesimal rotation about the sort of y-axis. This is the infinitesimal rotation about the z-axis. And this is a standard basis vector. Then we can collect them all together, the curvatures in terms of a matrix C. Then the complicated looking differential equations in the previous page neatly fall into this matrix differential equation. Okay? So you should think of the generative model as just this matrix differential equation with input variables, namely the nu, the speed, and the two curvatures. Okay. So this is one generative model, but one can write down other generative models. And in fact, this brings me to one that is very natural. I have deliberately used here Roman fonts to not get confused with the italic font we used in the previous line. So what are these equations? Very straightforward, right? The position derivative is velocity. Velocity derivative is acceleration. Acceleration derivative is what we denote as u, the jerk. Okay. Now, if you're interested in what the fourth derivative is, I learned that it's called snap. So I don't know what higher derivatives are called, but these terminologies show up in a very prominent way in biomechanics, and I will make a few remarks about that. Now, if you want to relate these quantities, which essentially tell us how the jerk is converted into position as a function of time, how is it converted? In fact, it's three integrators in a series, right? Three block integrators. Okay, and this is a linear system model with input being the jerk. In contrast, the previous equation, even though it looks sort of simple, the G multiplies the variables containing the U and V, and therein lies the major difficulty. This is a nonlinear model, not a multiplicative model. So when you want to extract the G dependence of the U and V, the corresponding representations are either multiplicative series or infinite series involving iterated integrals of the UV quantities. So it's definitely a nonlinear model. The model I wrote down in this slide is actually a very nice linear model with the jerk as the input. And now we could ask, was there a dictionary relating the one model's inputs with the other model's input? So acceleration is related to the speed derivative and the speed squared, etc. by this formula. Here I wanted to point out that the nu, u, v, etc. are scalars. The x, y, z are the vectors, the unit vectors in the triad. The portion of the acceleration that is orthogonal to the velocity direction, so we call this the lateral acceleration. That's just this component. Okay, just think of these two things. Then the third derivative, the third derivative of position, or the derivative of the acceleration, is the jerk. That's given by this messy formula. Okay, so you can see that if you start with a linear model like this, its inputs, however, are related to the previously pointed out model, namely the nonlinear model, in a complicated way. And there is a price to pay for this complication. Okay. So now comes a statement of what the inverse problem is of this subject. So the inverse problem is simply saying that, look, if I don't have the actual curves of the evader or the pursuer or any one of the star lengths, instead I have sample points in this curve, then how can I extract? So you go back to one of the models, say the generative model that I started out with the first one, and I want to know how to extract the u, the v, the nu. Okay. So the main thing is that the point of this extraction is that I want to connect the dots, perhaps, by means of a curve. In particular, I want the curve to be reasonably smooth. In fact, I may not even want to connect the dots exactly. Why is that? Well, that's because the data is noisy, so it doesn't make a whole lot of sense to claim that the reconstructed curve exactly passes through the data point. So what we say is that, well, we care about producing a curve gamma, which in fact satisfies the generative model of the couple of slides ago. I want to remind you, this generative model. Yes, Andre?
Are you assuming that you know which form belongs to which bird?
Yeah. Oh, that's a big problem. In particular, when we want to attack these kinds of inverse problems, we have already had someone help us and solve a sort of a data preparation where the information coming from multiple cameras has been run through some vision software so that you can establish correspondence between a point here and a point here at the same instant of time, and then next instant of time. So both spatial and temporal matching has to have been done. And we're still left with sample data, but this is sample data in 3 dimensions as opposed to the 2-dimensional data you get from cameras. Okay? So knowing all of that for each bird, all right, so we are handed a set of files which contain, say, 150 columns or 600 columns. Each column contains temporal locations at certain number of certain time intervals for one bird. So the point is that the reconstruction problem starts when you have that handed to you and you want to produce a continuous trajectory. So here what we're saying is that now we want to solve an optimization problem. The reasoning here is that, look, I want to solve an optimization problem in which the fit error of the smooth curve is given by this. I want to trade that against another term here, and this term is interpreted in the following way. When we thought in terms of bats, we said, well, it's really hard for the bat to change its trajectory curvature from period to period, in the sense that it's costly in order to either increase the curvature or to straighten out. So then rate of change of curvature is then entering into this problem, okay, as a part of the penalty for similarly the speed rate. So if you can help, if you can get away with it, you would like to have the curvature maintained constant. Of course, that's only happening over intersample times. And so the whole problem is then you're solving a constrained optimization problem where you solve this, you take this objective function and you minimize it with respect to curves that are generated by u v nu, satisfying the generative equation that I had before. Well, the thing we do though is that because those u v nu equations are quite nice, namely these equations in which we have the rotation group enter, etc. If you assume that sample to sample in the intersample interval the curvatures are constant, then you can do integration analytically in terms of elementary functions, because this is just rotation matrices that you are trying to calculate, okay? And so another way of thinking of it is you're computing matrix exponentials if the curvatures and speed are constant over the inner sample times, all right? So then once you do that, then this problem of optimization ends up becoming an unconstrained problem where you pretend that this integral has been replaced by a sum, a discrete approximation, and in the, well, for instance, if you use the same resolution as the sampling process, then in that case the curvature is viewed as constant over inner sample times, or if not, it could be viewed as constant over half the inner sample time, and so forth. And then we can plug in the explicit exponential formulas, and then we are able to attack this problem by using a standard routine like f min u and c, as opposed to f min com or something in MATLAB that people routinely use for constrained optimization problems. Well, there are lots and lots of questions, but do you even know whether there is this problem? This problem certainly has a generative model that is nonlinear, and even though this cost function looks moderately straightforward, so you have no real sense of the existence questions about this problem, right? I mean, you don't really know whether this minimizer exists or it's and you can keep getting better and better, okay? So you use some sort of steepest descent techniques here, and then that leads us to some cost reduction, but and we have stopping rules and so forth. We don't really know if we have ended up at some local minimum. So there are lots of difficulties with respect to extracting curvatures in the generative model. But the reasoning, yes.
How is down the relative economics?
Oh, I'm going to come to that in a second. And so this lambda, as you thanks for mentioning that. So it's sometimes referred to, going back to the early work in inverse problems by various people, Tikhonov and and others, as a regularization parameter or penalty parameter. And this is called the regularization term. All that it has done is to take a problem for which we have, which is ill-posed, we have infinitely many solutions, and tries to replace that by a better posed problem. And the question is, well, lambda should be big. Well, yes.
Shouldn't the coverage model of one word depend on the coverage model of the other, which is one is tracking the other?
Well, so what we would like to do is to extract the actual curvatures for each bird from its own trajectory. And then you're right that the interaction of the bird with bird means that the curvature program of one bird will reflect some regularity, like if it's close enough, there will be some alignment or similarity, and those laws have to be uncovered as well. You have to produce some hypothetical feedback laws and see to what extent your reconstruction supports your hypothesis or not. So coming back to Isaac's question, one want to say that if your data is very noisy, then you want to give less weight to this fit cost and more weight to the smoothness. So that means the lambda should be larger in that case. But that's just heuristic. There is a very formal process by which you can determine an estimate of lambda. It's called cross-validation. And the roots of that technique go a long way back to the late 60s and 70s, the work of Grace Waba and other statisticians. And I'll mention that in a moment. Okay. I want to point out, though, that in contrast to this problem that we discussed a moment ago, there is an alternative problem going back to the linear system model, the jerk model, where we had the generative model was just simply 3 integrators in a sequence driven by jerk. So then in this setting, a natural question to ask is, can we consider a cost function for this ill-posed problem, which is a fit plus an extra term, which is weighted version of the quantity here that's called the jerk path integral. This is obvious integration of the jerk cost. So this involves the third derivative of position. Now, looking at it as a controls person, you would say, well, I have a linear system, look at the quadratic cost, and however, there is these terms that are data dependent, the lambda k's are data dependent, and perhaps I could use my control theoretic technique so that I don't have to solve this problem by nonlinear programming and instead do some method that involves control theoretic calculation. Yes?
Along the line of Anko's question, would it make sense to add one more term which would try to minimize the difference between the curvature of 2 nearby birds or the neighbors of the given bird?
Yeah. Oh, you can make this cost function more interesting and more challenging, and argue for its reasonableness in various ways. And we have considered some of these things, but this is sort of the basic version of it. And I'll try to point out there is a body of literature that our colleague Bill Levine has paid attention to and contributed to for many years, namely the problems of high performance biomechanical activity, where performance is somehow measured in terms of cost functions like this and maybe others. And these inverse problems that people, including Bill Levine and others on this campus have studied, have a long history, and in fact, going back to the 1980s and even before, folks have said things like, well, if I'm going to reach for a coffee cup, there is infinitely many ways I could do that, okay? But somehow, if you pictured me, videotaped me, and took measurements, most of my trajectories will fall into some pattern. And I would like to find out about this pattern. And way back in the 20s and the 30s, Nikolai Bernstein, a physiologist, a Russian physiologist, actually contributed hugely to this field, and he formulated the idea that, well, look, if I need to move my arm in a particular way, I have various joints and muscles that I have to recruit to get the job done. It's a huge number of degrees of freedom for a task, particular task. So a big part of what the brain does is to impose constraints, or essential constraints, in order to eliminate this extra freedom. Well, so that was one hypothesis, and this is sometimes referred to as a synergy theory. Synergy here refers to the Greek term for working together. All the muscles and joints work together. Later, Gelfand and Zetlin, and more recently, a professor in mechanics of movement in Penn State, Latash, and others, many others, have paid attention to the same question, but proposed other hypotheses about how we resolve the redundancy. Okay? So the bottom line is that in the work of Flash and Hogan and others, the idea is that you don't resolve the redundancy just by imposing constraints willy-nilly. Instead, you make your choice of trajectory that solves the problem optimal in some sense. And it has been proposed that this jerk path integral is a reasonable cost function. In fact, yes, John.
Okay, you have to estimate the sequence, right, of curvature.
So
So
when we talk about this model,
yeah.
we have the jerk model,
But
namely
your
the
control
three
variable-
integrators model.
Yeah, the control variable you have to estimate are the curvature, right?
No. Here, the control variable becomes just the jerk vector.
In the previous model.
So these
The
two
question,
generative
the
models
question I want to raise, there are no constraints on each one of them and between them,
between the curvatures.
and in each of them.
This is, you mean between the birds?
No, just one single trajectory, because you know, you have the kinematics of someone, because you're trying to say that I'm trying to generate a model that will give me that curve. One way to put various kinds of models of kinematics is to actually put constraints on the curvatures that can be generated by the generated model. Either instantaneously for each one of them or in relation to them.
So what we are saying is that if you...
In other words, if I look at actual birds,
Yeah.
you cannot get any crazy curve you want.
So what we are saying is that the... remember our generative model here, okay? If I knew the full curve, then I can extract from it the curvatures by a certain complicated algorithm, but it is still a doable job. I only have a sample curve, okay? So I'm asking, what is the most plausible curvature program as a function of time that is consistent with this sample data? So I say the way to measure consistency is to minimize this, namely the fit cost, plus something that penalizes high derivatives, high rates of change
I
in the
understand
curvature.
that by that.
Now, if you want to impose additional constraints on the curvature, you could. Offhand, I don't have candidates for such curvatures.
Yeah, the regular.
This is the bottom of the barrel.
The question is, because you said the problem is unconstrained, that's what I'm questioning. Is it really unconstrained or there should be constrained?
Oh,
No.
this is
Generalization is different.
but it, no,
The
it-
constraint versus unconstrained came about there because, remember, this is all subject to the generative model. But the generative model is a nonlinear model. And so the question is, when I want to include that equality constraint associated with the generative model, can I really run something like this, which is an unconstrained optimization routine? So the way to think about it is that, well, we can integrate the generative model by means of matrix exponentials.
Right.
Then we got rid of the gamma out of that, and we only have the u let up. Okay, so in other words, we've sort of calculated out the constraint. We have not tossed it away, we just accounted for it by integration. Provided, I hypothesize that in the inner sample interval, the curvatures are constant. If the curvatures are constant, the speeds are constant, then the problem of integration is just matrix exponentiation. And that's, in this setting, with skew-symmetric matrices, etc., it is trivial. Okay? So that's what I meant by getting rid of the equality constraint. Okay? So then it became an unconstrained problem. But you could, as you said, have additional constraints such as, for instance, if you made this bird fly in a room, increasingly narrow room, a passageway, then large curvatures would be unlikely because it would crash into the wall. So that's part of the behavior of the bird in response to the environment. So here we are looking at it in sort of free space. Okay. John, Bill, do you have something more?
no, that's fine.
Okay. So the point is that there is one horrible looking nonlinear optimization problem, and then on the other hand, this quadratic optimal control problem with the linear system. And I mentioned to you this very interesting work of these neuroscientists. I want to make one more remark here. Why this jerk pattern integral is interesting in more recent times. Well, people have observed that when I move my arm around to reach the coffee cup, I have to send the joints off from rest to rest. In between, they speed up and then they slow down. So this question is really, are there any irregularities between the speeding up and the slowing down and the curvatures of the curve traced by the arm? Or when you ask me to write a piece of text by cursive writing on a piece of paper, and take a point on my wrist or my hand, how does it move? So people have observed that there are some scaling laws. Namely, if I'm making a sharp turn, then my speed goes down. If I'm making a more or less straight path, then the speed can go up. So if you plot log of speed versus log of classical curvature, which is a positive quantity, then there is the relation between those two ends up looking like a curve with a negative slope, in fact a straight line, and the exponent or the slope turns out to be minus 1/3, and so, or log of that. So as a result, this is sometimes referred to as the 2/3 power law in movement of human movement, hand movement, and arm movement. And there is plenty of evidence for this, and the question was, why is it there? And so people have argued that such an optimization is in fact the thing that leads up to such 2/3 power law. So people have given a certain amount of weight to this optimization. Okay, so moving on, I am very low on time. And so the idea is that to go back to Professor Marcos's question, how do you determine lambda? So there is a tool that people use in learning theory, which is that, look, if I have n data points and I have a parameter, what I'm going to do is I'm going to use only n minus 1 of them and do a fit based on those n minus 1 data points for a particular value of the parameter, and then test that fit on the one that I left out. Okay, that's what this is doing here. This expression is exactly telling you leave one out and fit for a particular lambda, and then use the associated curve to make a prediction of the one that you left out, and then do that for every one you can leave out. Okay, so there are n of them, or n plus 1 of them, and then this expression here roughly plays the role of an average deviation, standard deviation like thing. Okay, so it is, in some sense, if you set it up properly stochastically, it's like a sample estimate of a variance associated with a prediction. So then the idea is that what lambda should you pick? Well, pick a lambda that minimizes this sample estimate of the variance of the prediction error. And this is a long history in system theory, this type of thinking, the problem of bias variance trade-off, the problem of order determination for time series, all sorts of other problems where you have to estimate parameters. So this process that I just described is called ordinary cross-validation, and it's very time-consuming because you have to run an optimization problem many times and get dependence on lambda over a whole set of lambda values. Okay, so let me go quickly and say that doing things like this, in fact, in the MATLAB data, allowed us to infer that there is high correlation between certain theoretical feedback laws that I denote here and observed curvatures of a bat. And it's not clear all the details of this picture. I want to skip that. Another way to think about this theoretical feedback law is that the lateral acceleration of the bat going after a target insect is governed by a certain pair of things. One is its own velocity, and the other one is the rate at which the joint line connecting the bat and the insect rotates. And it's called the line of sight angular velocity. So this theoretical feedback law that shows up in many contexts, even variations of this show up in missile guidance, if you want to know how a missile goes after a target, and the way it is guided. And so it seems that there is strong evidence that with a certain reasonable, biomechanically reasonable delay, the bat is able to run this feedback law and still be able to reach close enough to the target so that it can capture it. So this is an example of how you put this kind of extraction of the detailed curvatures and continuous time information to use in order to sort of understand things. Okay? So in order to do similar things for a whole population of birds and be able to extract this with varying neighborhoods, it's a challenging task, and that's one of the things that we've been working on for some time. Matteo Mischiari's thesis, for instance, has some analysis of this kind. So what I want to do is to go back and tell you that these nonlinear programming problems that we have to do numerically. We have to do this constrained optimization numerically, and when we are dealing with curvatures, could we get around them by using this alternative model, this second generative model, which is a linear model with a quadratic cost? Well, control theory thinking tells us that you should use some optimal control theory pertinent to this context. And brief lesson in optimal control is that in optimal control problems, we deal with models like this, differential equations with inputs. So-called fixed free problem is specified by its initial condition x naught, and then there is a cost function associated with the terminal state you end up in, how far it is from the specified x1. This would be like the target for the dragonfly, and then there is a running cost associated with your trajectory and your input. So if you want to solve this optimization problem, our masters in our field a long time ago gave us a certain way to do this, which does not require calculus of variation, does not require invocation of necessary conditions and this and that. It's a bare hands goes and does something, namely completion of squares. How does it do this? Well, here's a couple of explicit formulas one can write down. this k here is a time function. These are all time functions. If you have any reasonable k so that it has a derivative, and if you computed this expression that I have here, or if you computed this expression, take its integral, then that expression by its own involves both u variable and x variable. But if the u and the x are related by the equation x star is equal to x plus du, i.e. along trajectories of that equation, if you look at these integrals, they turn out to be integrals of exact differentials. So they only depend on endpoints. So then if you apply the endpoint values, then you get 0, okay? So when you get these two expressions, 0 and 0, and you add that to the original cost you have no change, okay? And the k here is completely arbitrary in the face of it, except that it has to be differentiable. Now comes the smart, and that is that if you chose your k smartly, and we satisfy a certain matrix equation, the matrix Riccati equation, and the eta satisfies a certain linear equation, with some boundary conditions specified by the problem, then this choice of input, in fact, optimizes the cost function of Ju, and the minimum value is this, okay? This is a clear statement, and is done entirely through completion of squares. Okay, moving on. Instead of having one point fixed and one point free, if you have both points free, so imagine, for instance, the dragonfly sitting on the perch. It initially needs to figure out which way to look before it starts out. So it's sort of setting up its initial conditions, okay? In order to minimize the overall cost, let's imagine something like this is happening. So that's the metaphor for this cost functional. There's an initial cost, there's a terminal cost. The initial condition and the terminal condition are not determined except by the differential equation and the optimization problem. x0 and x1 are given parameters. And so then you ask, what is the solution to this optimization problem? Well, you plug in the same u-op as you had before, but then that gives you this cost. This still leaves you with an initial condition xt0. The best initial condition is then this, provided there is a positive definiteness assumption. Okay, so then you get a unique minimizer. This methodology that I just gave you is what is known as the completion of squares trick to solve the free problem. Now, one more comment. If you go back what I had before, you remember this optimal control had a very specific form. And I'm going to make a definition. That thing in the parentheses, I'm going to call it P. Then with that definition, the control has this form. And then immediately you can show by just differentiation that x and p satisfies this system of equations, where this system has a very important property. The system is very much a mirror of the equation that we see in mechanics, classical mechanics, where we write down equations for position and momentum. That's the analog here of x and p. And there is a certain function, the Hamiltonian, such that in terms of the Hamiltonian, the right-hand sides of this equation are really nothing but the first partial of the Hamiltonian relative to p, and the negative of the first partial of the Hamiltonian with respect to x. And the h, the Hamiltonian, is this. So in mechanics problems, this Hamiltonian would be nothing but, say, kinetic plus potential. But in the present context, we're solving an optimal control problem. But this Hamiltonian system, especially if the ABL, etc., are constant, is easy to integrate using exponentials. So the point of these remarks is that in this setting, you don't need to do any ugly numerical stuff. Exploit these analytical formulas. So what does this have to do with the maximum principle? Well, the whole point is that when you have more general, this is a very crude and in-words statement of what the import of the maximum principle is. It says that if you have more general dynamical systems and optimization criteria, the maximum principle says that there is a function called the free Hamiltonian, which is built out of various quantities, position, momentum, or state, co-state, and control. And that function is optimized by your optimal control, provided you know the optimal control. So this is a big provided, okay? And then comes an associated Hamiltonian system, just like we did in the previous slide. Okay, now we go back to the data analysis question. If I now had n data points, each of them is denoted by xi, I equal to 1 to n, then can I fit a linear system model to it, which is a generalization of the jerk model, right? The jerk model corresponds to an A matrix being more special. associated with the triple integrator, and the B matrix is also special. So the general problem of linear system fitting to data, where the data is noisy, so you don't necessarily pass exactly through the data, you have a fit error, and then you also balance that against a certain cost associated with the input going in and the state. If you did this, then associated optimal control looks like the very same pattern that we had before. Now, there's the Riccati equation guy that comes in here is something that has to adjust its boundary conditions. There are so-called jump conditions, okay? So the main idea then is that in order to solve problems of inversion using these jerk models, we need to resort to Riccati equations, and we like them. They're friendly, they're familiar, and they're very tractable. Okay. So the main message there is that if only you use linear models with the jerk as the input and the jerk path integral as the smoothness cost, in smoothness terms the cost functional, then you wouldn't have to do complicated numerical optimization. So why don't you do that, right? That's good, and be done with it. But the point is that the expressions for acceleration and jerk, etc., relate to the expressions for curvature and speed, etc., in a complicated way. I showed you many slides ago. And if you decide that the individual agent, bird or bat or dragonfly, is really managing to control its steering, its curvature, it doesn't know really anything about its jerk, okay? I.e., its wing beats and the body shape produce steering when it's facing the oncoming wind, and it manages to adjust things guided by its vision of a target. So that's where we hypothesize that curvature or steering rate is really the control variable. Now, if you change the rules of the game and said you should think of the jerk as your control variable and made the problem easy, you still have the task of justifying in that context the jerk path integral. So there are two places where we can sit and do this problem. One place has one kind of justification. The jerk path integral certainly has a long history of biomechanical relevance. So anyway, I want to leave it at that. But the question really is any of this generalizable to the nonlinear settings that we started out with? And it turns out that yes, it is. If you had a symmetrical setting where your curve equation is gamma dot equal to u and the control is this, and this cost is nothing but trying to connect n data points by means of lines that do not necessarily go exactly through the data point, but stay close enough to it. That's the smoothness, the fit cost. And then this tells you that you should connect them by straight lines, okay, because you're trying to minimize path length in Euclidean space. However, it tells you that the lines should have slopes that be changing at precisely those places where you have data, okay? So the data, in fact, gives us the slope jump. And so that's for lines. So then more generally, if you're dealing with not straight lines and Euclidean space, where you know straight lines are the natural shortest paths, instead you're dealing with surfaces of some sort, manifolds. And then there you have an inner product that measures velocity or, the speed, etc. in a point-dependent way. Then the problem gets more complicated. And it's a problem in Riemannian geometry. And the appropriate necessary conditions are what are called the geodesic equations, and again, jump conditions. And this is a cost that is the fit cost. So finally, this brings me marching to what is called I'm going to sort of say a couple more words, and there's no reason to rush everything and attempt to, I'm going to save myself for some questions. So the main idea is that the original problem he set up in terms of curvature as the input and the generative model given by the frame equations, we can go back to that and ask, okay, you got lucky with the linear quadratic setup involving the jerk path integral and the jerk input. You could attack it by Riccati equations. Is there a certain explicitly solvable optimal control problem associated with the original generative model involving curvatures? So that's the problem that I want to go after, and we have made some progress in that area. And so there, the point is that the underlying space on which the control problem is defined is no longer just Euclidean space, it is the space of matrices that stand for rigid motions. And moreover, on that space, one can ask what is the nature of the cost. The cost functionals we've been writing down actually have some symmetry. They have what I call left invariant cost functional. So in this case, one can show that the problem in very special settings with, say, for 2 endpoints, for instance, only 2 pieces of data, it's easily integrable by means of elliptic functions, okay? Jacobi's elliptic function. So if you are as comfortable with elliptic functions as you are with sines, cosines, and exponentials, then you could claim that you solved the problem in an integrable way. And of course, once you have not 2 points, but n points, or n plus 1 points, which are data points, then you have to introduce jump conditions. So that turns out to be a more complicated story. And all of this is really ongoing work in Vishwadeep Day's thesis, in this thesis proposal, etc. And I want to leave it at that instead of rushing, and just mention that much of our work is based on some prior work, and also early work by Reddy, who wrote a thesis on precisely this class of inverse problems. And that's the end of the story, and if you have questions, I'll be happy. Thank you.
Time for new questions.
Okay, so if I take the movies you saw, right, and I'm trying to understand that behavior, the major unanswered question, or at least I don't know the answer, is what is the collaboration signaling between the birds? Because you know there's evidence that if you assume the usually assumed model of nearest neighbor communication, you can never explain the fast patterns that we saw. So how can I use this technique to try to understand how they coordinate? Because why I'm getting it is that, and it's related to the previous question I asked you, is that you're going to have to put some constraints between the birds themselves and the neighborhood and all that stuff to try to understand coordination. And then you have a hope. But is that solution method scalable to that level?
So, first thing is that when the problem of extracting the raw geometric input associated with these bird trajectories, which are sampled, we treat it as an individual bird problem, okay? Because the curvatures or jerk, whatever you, is its own business, okay? However, those inputs that it supposedly commands its autopilot or implements are in fact not arbitrary, but in some sense related to the relative positions of the other birds in some notion of neighborhood, because otherwise you don't get any kind of cohesion. And they have somehow evolved evolved to be doing some things like that in order to achieve cohesion. So, I see you're shaking your head, and I know that you could have accidental cohesion without, in some sense.
I'm not saying my head for that.
All right, let me go back to what I was saying. Okay, so the thing is that the problem of inverting trajectories to produce the inputs is not a problem that needs to take into account any visibility constraints or anything like that. You can do it on the curve by curve basis. If you could, you might say that just like in physics, if you have a bunch of interacting moments in a magnetic setting or something like that, then somehow they affect each other. So if you want to solve a problem associated with one moment, you could do so perhaps better by doing it for all of them in some big gigantic optimization.
Well,
we don't want to do that.
To make the question even more clear, suppose you do everything you say. You have the multiple cameras, you target the birds, you know the individual trajectory, you do the inversion, you find the curvature for each
bird, yeah.
For each bird. Now you go to the next step. I want to find a relationship between
Yes.
the birds, right?
Which is what we do in our work.
So I'm saying, how is that done? And why the patterns? Because there you have to try to associate birds either in neighborhoods or partial neighborhoods or long-term communications or what they see as for the rest of the ensemble. there's a large number of questions that we have
Yeah.
the foggiest idea, right? What happens to explain this
So
very
then
fast.
we have some idea. So what is the idea? What that we now have in the literature?
That's what I want to hear. Yeah.
So the European Star Flag project, which goes back to 04, 05, and ended, well, maybe 07, and ended a year or two ago, has yielded some insights. I mean, as is the case in biology, there are always competing viewpoints. But the one story that this is standing up against is that historically in the flocking or swarming literature, as represented by the work of people like Ian Kazin and others, this notion called zonal behavior, which is that you imagine each bird or animal has a little disc around it, and that disc is carved up into certain sectors. And if there is another bird or animal comes into a particular sector, you want to align with it, or you may want to avoid it because it's too close. You know, that single disk is also divided into sub-disks. So this view of metrical neighborhoods has been challenged by some of the analysis of the data coming from the Star Flag project. And the argument made is that, look, the bird has limited capacity to pay attention to other birds, and the evidence through some statistical analysis, it suggests that, I mean, this statistical analysis simply uses position and velocity data. Velocity estimated crudely from the data. And it says that essentially the bird pays attention to a small number, 5 to 7 other birds, which are nearest neighbors. Okay, the closest bird and the next closest, and the exact disk in which it lives doesn't matter. Okay, within reason, right? And then beyond that, if there are, for instance, you pick an arbitrary disk and you have 50 birds in that disk, okay, if you take the metrical neighborhood notion, it's not going to pay attention to all 50. Okay, so that's so it's called the topological neighborhood idea as opposed to the metrical neighborhood idea. So the Cabana and company paper in PNAS in 2008 was devoted to this idea. And this program continues, and we have tried to extract the curvatures for small flocks, about 150 or so, and see to what extent the observed curvatures of different birds are related by some rules that are consistent with this topological neighborhood idea. Okay, so that's a story that is partially told in a thesis by Davis Getty, but that's the full story is going to emerge in the
So what is the key idea? If you take the trajectory and you find the curvature of all the individual birds, you try to identify the ones that they influence each other. Would you look at the curvature to be close to each other, or what is it?
Well, so we have done many measures, including, for instance, we could do correlation analysis where I could say that when you turn, I also turn. In other words, I match curvatures, for instance. I mean, is that true? So we have done correlation analysis. We've done other measures as well, even using velocity correlation. So you don't have to have curvature correlation. So, it's still work in development.
Thank you.
So, and also, I want to emphasize, one of the reasons why we're working very hard at this reconstruction problem is that there's high sensitivity to the results of the reconstruction. So, for instance, these lambda parameter, etc., really influence what curvatures you produce. You may produce reasonable looking curves, but the actual curvatures may be dramatically off between two possible choices, and this is because you chose a lambda that isn't quite consistent with the noise parameters and such. So this is what we want to overcome, and that means we have to solve the cross-validation problem. That's a very time-consuming problem, and we're working on that.
Thank you.
I think there was a question.
In the language of the pursuer and the targets, there's an underlying game being played.
Yes, thank you.
Each group is trying to survive in its own way.
If you think of predator to prey,
Predator prey. So there is a predator on the one hand, at least a subset of the prey. They're playing some kind of game. Is there some understanding of it which can help in the formulation, or does it make things more complicated?
Well, I mean, the very roots of trying to understand flocking and swarming have been influenced by ideas like, okay, so the creature is form groups in order to reduce the probability of being caught or attacked by the peregrine falcon, for instance. And so these kinds of hints are really gross geometrical hints. It doesn't tell you much about the details of what's going on. For instance, the peregrine falcon is at one edge of the flock. An action is taken by one of the members of the flock, which actually sees the falcon because it's close enough to it. And then its change in direction is somehow telegraphed to the other birds, and they also do the same thing because of their neighborhood rules. They don't see the falcon, but it is really that kind of cascading effect which we see produce the kind of patterns that we see.
Sure.
So now, with regard to any kind of competition or game aspects, in the present instance, at least in the kind of data that I've come up with, that's not. Yeah. But I had analyzed, as you probably remember, in the bat insect story, multiple strategies and which strategy is better, and that was done using some evolutionary game analysis. But that sort of takes us off. Yes.
So has this strategy helped in the data assimilation problem, in the sense that if you develop some hypothesis about control, can you use them to use data association, address inclusions while you post-processing the data set to generate the trajectories?
So, it's a kind of alternating process in the sense that, it's a bit like if maybe EM or something, in the sense that if you have a hypothesis, then you plug it in, and then you get, if you were to plug that in and then now solve not trajectory by trajectory, but bundles of trajectory by bundles of trajectory, okay? Then that's a more complicated optimization problem, but you might think that the answer that emerges out of it is more trustworthy. But then you have to now feed that back into your hypothesis testing process. So at this stage, the problems are hard enough for optimization trajectory by trajectory. And we have kept that separate. Okay? So in other words, we want to do the numerical problem of reconstruction well, in its own right, using numerically based cost functionals, which involve fit and smoothness in one sense or the other, whether smoothness in the sense of jerk path integral or in terms of the curvature derivative path integral. But then once we do that curve by curve, then we think, when we've done that reasonably well, then they say, okay, now we're ready. So one of the exercises that we're going through, there is a colleague, as I mentioned, Leonardo, who studies dragonfly behavior. And he has his own methods of reconstruction, very close to our linear technique. In fact, some of you may know some of these filtering techniques in digital signal processing called Savinsky-Golay filters. What they do is take data and produce a fairly reliable way of differentiating the data. Okay? And they are sort of filter derivatives. And this has its roots in some sort of spectroscopy work back in the 60s. And that technique has yielded some reconstructions of dragonfly trajectories. And then our techniques based on curvatures are head-to-head against that technique. So we're now trying to figure out why are these differences? Is our lambda parameter not good enough, for instance? So it's at that level we are operating.
Gil and then Bill.
So implicitly, are you assuming the animal's trajectory is optimal in some way?
So
Using optimal control methods to reconstruct the trajectory, are you assuming that the trajectory itself is optimal?
So okay, when we set out to do the reconstruction using the frame method and generative model of that type and curvature path integral, the only reason to have that penalty term and doing optimization has to do with assuring ourselves some sufficient smoothness and also to regularize the O-post problem. There was no fundamental optimality that we wanted to demand of the behavior of the animals. The contrast a little, and then in the same spirit, we could have replaced that by this linear quadratic problem, the jerk pattern and all. Again, viewed from the point of view of adding a penalty term to regularize the problem. But then, as I mentioned, in the biomechanical literature and physiology and movement literature, there's a lot of emphasis on this optimization of the jerk pattern as being something that happens in arm movements, hand movements, and then actually body movements even. So recently I did a paper in which people walking in a room, given various exits to go to, and they do so, and you look at their trajectories, it appears that their path, body movements, say the center of mass of the body or something like that, during ordinary walking, seems to obey some such optimality. Well, the question is, what is the source? The scaling law or the optimality? The suggestion is that optimality is more fundamental than the scaling laws. And the scaling laws are sort of derived consequences. So it's two different worlds we occupy. From the point of view of numerical inversion, we're not committed to doing this as a kind of fundamental optimization criteria. We could use other criteria.
Can I have a follow-up, please? Sure. Susan. Every time I simulate blocks, I get this beautiful, elegant flow that will say star. Not even close. Have you ever been able to accomplish that? And the other issue is sometimes the flock breaks apart, widely apart.
Yes.
Way beyond this radius, and then it reassembles. So that's a different mechanism.
So you saw that happen in the case of the particular Stalin flock, and it has a lot to do with, so if you look at a flocking event over a comparatively short period of time, then you can see some coherent structure. But then over time, the animals are influenced by what's in the environment, predators, or even the visual input they get from buildings or what have you. And then and also notice in the implementation of certain steering laws. They don't exactly steer this way, they introduce noise. So the suggestions that have been made is that it is really the interaction of external stimuli and noise that cause this more complicated behaviors. And putting those things into simulations is doable to elicit this kind of behavior. But we haven't been so driven as much as really focusing a lot on, okay, we have this particular flock, and we have this reconstruction, and we want to analyze the data before we even do additional synthesis. So, what goes on here? So that's the kind of thing. So the dynamical questions that you're asking would suggest some kind of flow or bifurcation phenomenon or something, possibly next stage. But for us, the models are really only important insofar as the models can be used to say that certain decision variables are governed by certain interactions with the neighbors. So the curvature is chosen as decision variable. So in other words, the models are only so important as for us to uncover mechanisms that we think are reasonable and see whether or not they are supported by the data. So the forward modeling and simulation question that you're asking has not been central to my thinking.
Bill. In your analysis of the predator-prey situation, you actually accounted for the delay in the bat's sensory apparatus. You would think that this would be even more crucial in the flocking situation. So do you have a sense of, for that collective problem, what is the delay between when a bird sees something and is able to act on it?
So in some computation that Biswa and Matteo had done, delays of the order of 30 milliseconds are observed. In some computation with dragonfly data, 25 milliseconds has been observed. Now,
hard to believe that a bird is that quick.
Well, so the dragonfly setting, talking to Robert Oldberg and listening to him give a talk, this number, 25 milliseconds, that didn't come up. Okay.
Yeah, I mean,
but the question really is, I'm not going to go to the bank with our current analysis of the numerical data on starling flocks.
is there data from the other side? I mean, you can do an experiment directly on a starling and from that, try to infer, what the sensory motor delay is.
It seems that, I've not seen that literature on avian interaction. Maybe it exists, but these are questions that still, I think, are open.
Yeah.
Even for bats, to know that these delays that we are observing as being reasonable for their numerical computation, 100 millisecond delays, that's really talking to a number of people who have done different kinds of experiments, which are really, the context is very different. Okay? So with neuronal delay, biomechanical delay, and other kinds of things. The echo delay is the smallest bit. It is not material in the laboratory.
No, in humans, the delay between sensory input and motor output has been extensively studied. And you get very different numbers depending on the sensory modality.
Yeah.
But that matters a lot in a flock. I mean, if you introduce enough delay, then there's simply no way that they don't collide.
Well, I mean, the question really is, what mechanism, so there are these mechanisms that we have proposed which have to do with ignoring collisions and simply saying that, okay, if we want to be approaching something or aligning with something, what feedback ought to be in place. But then modify that by adding terms that also allow you to veer away if you're too close. But what does too close mean? These things are not measuring range; they're measuring something else. So what do they measure? They measure looming cues, for instance. So it remains to be seen. So avoidance is already another level of complexity.
Just one comment. It's hard for me to believe that a creature that is flapping its wings is only steering. If you want an example where steering is really the control, you want to look at soaring birds, which really do, just simply float and adjust their curvature by just a simple tiny flick of a feather.
Yeah. So what you're saying is that there is all the usual details of drag and lift and propulsive mechanisms for speed, okay, speed change. They're all in place there. So, so the question really is, can you have reasonable support for even the steering part of the story?
Yeah, you have a lot of weight imposed on a very simple abstract model.
Yes.
And it's hard to be sure that there aren't details that are...
Point particle models certainly are about as simple as they get, and that's the bottom of the barrel. So, but even there, we have a lot of work ahead of us. And so, but the one important way in which one of the things you mentioned plays a role in our numerical work is that the ability to extract information that has to do with the harmonic components of the wing beat, and to see that in your numerical data. So for instance, if you have acceleration signals extracted or jerk signals extracted, do they have a harmonic component associated with wing beat frequency, for instance? So if not, then you somehow oversmooth the data or something like that. So these are all coming into play, but in an indirect way.
Wonderful. Let's thank our speaker. Krishna is going to stick around, so if you have more questions, please come forward and talk to him. And also, the president of the IAI is here for our students. If you want to talk to him.